I, yeah, these are the problems on work, energy, and power. And then the first one, you got to find the change in potential energy, which is mg times the change in height. That'll give you the change in potential energy. And of course, the minimum work required would be equal to the change in potential energy. So whenever you're lifting something, the change in potential energy is equal to the minimum work. And can the actual work done be more than this? Yes, because there are several resistive forces like air resistance and friction and all that, due to which energy is dissipated. So yes. And the second one, whenever you talk about stretching a spring, the force in the spring is K times delta X, where K is the spring constant.
New message arrived.
And therefore, you rearrange that to find the extension of the spring. And once you get the extension of the spring, that's in meters, so I've changed it into centimeters. And then, since it was originally at the 15 centimeter mark, add 46.23 to that to find where it will line up now. So that's 61.23 centimeter. In this question, the person who jumps is 3 meters above the trampoline. So the person has potential energy, and since he takes off at 5 meters per second, he also has kinetic energy. So just when he takes off, he has both potential and kinetic energy. But when he lands on the trampoline, his potential energy at that point is 0, because the height is 0 now, because you measured it from the trampoline. And so, using the conservation of energy, the kinetic plus potential at the top should be equal to the kinetic plus potential at the bottom. So you find the total of the kinetic energy and the potential energy, and that's when you get this. And therefore, the kinetic plus potential energy at the bottom should be equal to the total at the top. So equate them and calculate. Excuse me. When you take the square root of that, you get the answer as 9.15 meters per second. In the fourth one, again this problem has a second part. And to find out how far he depresses it, now you know that as soon as he hits the trampoline, all the kinetic energy is going to be converted into elastic potential energy of the trampoline. So on substitution, and taking the square root, you get it as 0.296 meter. Okay. Now this is the same problem. The kinetic energy at the top plus the potential energy, which gives you the total energy as given here. Total energy at the top should be equal to the total energy at the bottom. And at the bottom, the potential energy is 0 because the height is 0. Same thing. You don't have to care about the angle at which it is fired. Just take the potential and the kinetic, add them up. They must be equal at every point, in fact. So you get the answer as 198 meter per second. And for the fifth one, the spring stiffness constant is nothing but spring constant is given. It's compressed down, so it has elastic potential energy, and then you're going to let go. When you let go, all the elastic potential energy becomes converted into kinetic energy. So on rearranging and calculating the velocity, get it as 8.44 meter per second. And in the second part, how high will it fly? As it goes up, all this kinetic energy gets converted into potential energy. So at the highest point, all this gets converted into potential energy. Excuse me. And so you get the height as v squared by 2g. So the height is 3.634 meter. That's the height to which it will go. In the sixth question, the cyclist is going up a hill of 150 meter at 7.8 degrees. So to find the work done, just use MGH, because work in this case, he's lifting himself and the bicycle, so it's MGH. And now to find the force that he exerts, you have to divide the work done in each rotation of the pedals divided by the displacement in that rotation. So we got to find the work. We got to find the work in each rotation of the pedal divided by the displacement, which would be the circumference. Now that's what I'm doing here, and that was one way of doing it, but I think I'll do it in a different way, because, well, although finding the circumference is a must, and so here I'm finding the circumference. 2 pi r, and you get it. Actually, the work done, you get it as 107, as I'm going to show you. So that's an easier way to do it. When you take sine 7.8, you are able to get the displacement up the inclined plane. That's what x is now. For one rotation of the pedals, the displacement up would be 0.69 meter. Now therefore the work done during that displacement is 75 times hold on a minute. X is actually the height through which you go up, because what's given as 5.1, that's 5.1, and so this is the x, and you're trying to find x, and you get it as 0.69. meter, and then that's why I use 75 times 9.8 times 0.69 to get the work done during one rotation, and then divide that by the circumference to get the force applied. And the seventh one, the baseball has potential energy at the top, and as it falls and just before it hits the ground, all of it gets converted into kinetic energy. Potential at the top is equal to kinetic at the bottom. So on rearranging, you get the velocity. It's 15.96 meter per second. But that is without considering air resistance. But if it actually hits the ground with a speed of 8 meter per second, then you find the kinetic energy for that speed. And since it had a bigger potential energy at the top, which is given by mgh, you find that, you find the potential energy at the top. So now you know how much energy was lost. If you take the difference between the potential energy at the top and the kinetic at the bottom, you know how much work was done against the air resistance. So the energy lost is the difference. And since you know that work is force multiplied by distance, force multiplied by distance, so you can find the air resistance, which is the force, obviously. Okay, it's 13.83, so I'm changing it now. That was a calculation mistake. And so you get the air resistance is 1.06 newtons. In the next question, the skier reaches the foot of this incline and then glides up. So the kinetic energy on reaching the bottom is half mv squared. So you find the kinetic energy at the bottom in terms of the mass, and then find the potential energy at the top. The height is given as 12 point, no, the distance over the incline is 12.2, so you have to find the height. And once you find the height, mgh gives you the potential energy. And if you take the difference, you know how much work was done against friction. And then equate it to force times displacement to get the frictional force. And so it's the work divided by how much you actually moved, which was 12.2, so you get 2.87 mass. Remember, this is not meter, it's just a mass, because mass was not given. And then we have to find the coefficient of friction, so the normal reaction is mg cos theta. Coefficient of friction is the frictional force divided by the normal reaction, and the masses cancel out. You get 0.31. In the ninth one, Pretty straightforward question. Again, you have to find the height of the stairs using the angle. So you can find the increase in their potential energy, which is mgh. And then when you divide that by time, you get the power, because power is work over time. So you get 1047 joule per second, or watts. Okay. And the last question, the 10th one, the cyclist is coasting down, means moving at constant speed, therefore the net force is zero. That means there is friction that is stopping him from accelerating, okay, when he's coming down. Keeping that in mind, power is work over time, but work is force times displacement, and when you take displacement over time, you get velocity. So you have a new formula. It's power is work, power is force multiplied by velocity. But in this case, the force is mg sine theta, because you only need the component of weight acting down. So it's mg sine theta times 5 gives you the power. And this would have been the power required if there was no friction. But there is friction. And to correct it, if there is friction, what you have to remember is that you have to do twice the work. You need to have twice the power. Because when you're going up now, you are not only fighting against mg sine theta, you're also fighting against friction. And you know that the frictional force was exactly equal to mg sine theta when he was coming down. That's why the net force was equal. The net force was zero. So, therefore, you multiply by 2 to get the actual power. Well, I'm sorry for all those corrections that I had to make, and I did not want to redo it because it takes a long time anyway.